This video will cover solution stoichiometry and precipitation reactions. Here are the key concepts in solution stoichiometry, kind of the tips and tricks and key things to keep in mind. You're still relating products and reactants to each other using coefficients of balanced chemical equations. This would be what we call the mole ratios. So this is the ratio of coefficients in the balanced chemical equation. So you're saying, for example, for a certain moles of reactant B that reacts, you get a certain number of moles of A produced. So those are the coefficients of the balanced chemical equation. We've seen this before. You do the same thing with solution stoichiometry. The thing we're doing differently is we're using molarity as a conversion factor to convert between volume and moles. And I went over this in the video that came before this section. So here's our use of molarity as a conversion factor. So moles of some chemical A per liter to go from volume to moles. So when you do that, you multiply volume by molarity to get moles. And then you can go the other way. If you have moles and you want to find volume, you can multiply moles by 1 over molarity. So the moles are on the bottom and the liters are on the top because you want those moles to cancel so that you're left with liters. So this is the new piece in solution chemistry that you're adding in. And then we're still using molar mass to convert from grams to moles or moles to grams. So you've seen this before. So here's the use of molar mass to go from moles to mass, and then here's the inverse, 1 over molar mass to go from mass to moles. So these are all of the different skills you need to be able to use when you solve word problems for solution chemistry. And here's one example of a word problem. So this problem says, what volume in milliliters of a 0.150 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution to form dissolved sodium nitrate, carbon dioxide, and water. So the first thing you want to do for this problem is write the balanced chemical equation. So you're told that you've got nitric acid, HNO3. This is an acid that's dissolved in water, and that is reacting with sodium carbonate, which is also dissolved in water. And you know they're dissolved because what you're told is you have a solution of nitric acid and a solution of sodium carbonate. That's how I know to put these aqueous subscripts for the state or the phase of these two chemicals. And then what's being formed is sodium nitrate. That's going to be in dissolved form, and we'll go over solubility rules also in this video so you know how I know that you've got this dissolved form of sodium nitrate. Got carbon dioxide, and that's produced as a gas. And then you've got water, and water is a liquid in this case because this reaction is not occurring at a high temperature. If it were occurring at a high temperature, those water molecules might vaporize into the gas phase. And then before you can start this problem, the next thing you need to do is balance the equation. So to balance it, you'd put a 2 in front of the nitric acid and a 2 in front of the sodium nitrate. So now that it's balanced, you can solve this problem. So you want to start with the volume. And what you're going to do is multiply that by the molarity of the sodium carbonate, because you know this is the volume that you want to react. That's going to get you to moles of sodium carbonate, and then you can relate moles of sodium carbonate to moles of nitric acid using the balanced chemical equation for this. And then you can go back from moles of nitric acid using the molarity of nitric acid back to volume. So it's a multi-step process here. For these solution stoichiometry problems, you often end up with one really long dimensional analysis. So I'm going to do that. I'm going to start with the 35.7 milliliters of the sodium carbonate. I'm going to immediately convert to liters because I want to be able to use the molarity as a conversion factor. So here's the molarity of the sodium carbonate per liter. And then you're going to want to relate the sodium carbonate to the amount or the moles of nitric acid that react. So for every 1 mole of sodium carbonate that reacts, you have 2 moles of nitric acid reacting. Now you've got moles of nitric acid, right? Because moles of sodium carbonate cancel, liters cancel, milliliters cancel. And the last thing, now you want to go from moles of sodium nitrate to a volume. So you're going to use the molarity of sodium nitrate as a conversion factor here. So you're going to put the moles on the bottom this time. So you've got 0.150 moles of nitric acid per liter of nitric acid. So moles of nitric acid cancel out and you're almost there. You want your volume in milliliters. So you're just going to say in 1 liter, I have 1,000 milliliters. Liters cancel. And when you do all that math in your calculator, you end up with 51.4 milliliters of nitric acid solution. So there's the answer to this problem. So in this video, we're going to look at a specific type of reaction, a precipitation reaction. In this chapter, we'll also be looking at acid-base reactions and redox reactions. So there are 3 main types of reactions that occur in solution: precipitation, acid-base, and redox. So we'll look at all 3 of those in this chapter. The first one's precipitation. So a precipitation reaction is a certain type of reaction called a double displacement reaction. And I'll get to that in a minute. I'll show this example here and what I mean by double displacement. But before we get to that, just some basic terminology. So a precipitation reaction is a reaction that happens when 2 solutions are mixed, and what happens when you get precipitation is a solid forms. So the solid that forms in a precipitation reaction is called the precipitate. So this schematic here shows 2 different solutions being mixed together. You've got the potassium chromate and the barium nitrate. So these are the different ions that come with these 2 compounds here. And you can see all of them are in this beaker. And they're all floating around in solution in this beaker because you've just mixed the 2 solutions together and no precipitation has happened yet. But you can see what happens is that a precipitate forms. So you've got this chromium ion being part of this new solid, this ionic compound that's formed, and then you've got the barium ion here as part of this ionic compound. So this is a solid that's starting to form on the bottom of this beaker, and in reality this is what it looks like. You can see this barium chromate forming on the bottom of the beaker. So the precipitation reaction that happens here is you're mixing this potassium chromate, and it's a solution of potassium chromate. So the subscript there is aqueous. You're mixing it with a solution of barium nitrate, and that's aqueous. So when they mix together, what double displacement means is basically the ions switch place. So in this compound, this ionic compound, you've got two ions. You've got potassium and you've got chromate, which is a polyatomic ion. In the barium nitrate, you've got the barium cation, and then you've got the nitrate polyatomic ion. So what happens is they switch place in a double displacement. So now the chromium and the chromate and the barium will form an ionic compound, and then the potassium will hook up with the nitrate to form an ionic compound. So you just switch places. So the potassium nitrate will look like this, and you've got a coefficient of 2 there to balance it, and this will be aqueous. It remains dissolved. You can see the potassium and the nitrate. There's the potassium, there's the nitrate. They remain dissolved. They are soluble in this solution. The barium chromate is insoluble. It precipitates out. So when you form the barium chromate ionic compound, it looks like this, and the subscript's going to be solid because you get a precipitate there. So that's one example of a precipitation reaction. So how do you determine whether precipitation will occur or not? Two terms we need to go over first. Soluble means that something dissolves in water. It could be an ion, it could be a molecule, but whatever it is, it dissolves in water. It forms a homogeneous mixture, a solution. Something that's insoluble does not dissolve in water. Something that's insoluble precipitates. It forms a solid on the bottom of the beaker, just like that barium chromate did in the example on the previous slide. So here are the solubility rules. So this first part is under this heading. Compounds containing the following ions are generally soluble. So whenever a compound contains lithium, sodium, potassium, or ammonium, it's always soluble. Always. There are no exceptions. Similarly, whenever a ionic compound contains nitrate or the acetate polyatomic ion, it's also always soluble. There are no exceptions. So whenever you see any of these in a compound, no matter what it is paired with or bonded with to make the ionic compound, that compound is soluble. These next two rows, there are some exceptions. So generally, when you see chloride, bromide, and iodide in an ionic compound, it's soluble, but when any of those halides are paired with silver, this polyatomic of mercury, or lead, you're going to get insoluble. You're going to get precipitation. When sulfate is the anion in an ionic compound, it tends to be soluble, but when sulfate is paired with strontium, barium, lead, silver, or calcium, it's insoluble. It's going to form a precipitate. And then the next heading is compounds generally containing the following ions are insoluble. So these tend to be insoluble with a bunch of exceptions. So that's how this table works. If we go back to that question we just did, chromate, I guess chromate is not on here. So not all of them are here, and that's okay. We'll just move on to this one. This one will illustrate how to use that table. This one says, which solution forms a precipitate when mixed with a solution of sodium carbonate? Write the balanced chemical equation for each precipitation reaction. So for this problem, you're mixing each of these ionic compounds in solution with a sodium carbonate solution. And you're trying to predict whether a precipitate forms. So for the first one, the potassium nitrate and the sodium carbonate, you've got Na2CO3 aqueous. So that's always going to be what the sodium carbonate looks like. And then you've got potassium nitrate. Going to, and this is the double displacement, so the ions switch place. You have K2CO3 and we're going to use that table to determine whether they're aqueous or a solid. And then you've got sodium nitrate. So I'm just going to write the double displacement reactions first, and then we'll go back and determine if these products are going to have an aqueous subscript, meaning that they stay dissolved, or if they're going to have a solid subscript, which means they've precipitated. The second one is where sodium carbonate mixes with sodium bromide. So for this one, the double displacement reaction is Na2CO3 plus NaBr. So they're both solutions. Solutions are being mixed together, so when solutions are mixed together, the components of the solution are dissolved in the solution, so they're always aqueous. And then here, you've got, actually for this one, you've got the same products and reactants, because sodium is your cation in both cases. So you know that they're both aqueous because they're dissolved in a solution to start, so they're not going to precipitate when they're mixed together. You'll get some switching of ions in reality, which is what happens when you mix the solutions together, but you're going to get the same results, the same products as reactants. And this kind of thing can happen. The next one, you have, again, the sodium carbonate solution now mixed with the ammonium chloride. So ammonium chloride looks like this, and it's a solution of ammonium chloride, so it's aqueous. And when you switch the ions and do the double displacement, you end up with this plus NaCl. And then finally the last one, you have your sodium carbonate mixing with lead acetate, which looks like this. So we've got lead, the acetate anion, and then you switch places where you've got lead carbonate plus sodium acetate. Now let's flip back and forth between this slide and the table on the previous slide, because for the first, second, or third and fourth one, we're going to want to figure out the states or the phases or the subscripts for the products. We already know from the second one because you've got the same products as you do reactants, but for the others you had new products formed. So let's look at potassium and carbonate. If you go back to this table, you can look right away. Any compound that has potassium is soluble. So that's going to stay dissolved in solution. Similarly, any compound that has sodium or nitrate, here's the sodium, here's the nitrate, is soluble. So nothing will precipitate when you mix sodium carbonate and potassium nitrate together. Everything will stay dissolved in solution. It may not look like anything happens if you mixed those two solutions together, unless there was a color change or something like that. So for the next case, let's look at ammonium and carbonate. So ammonium, anything with ammonium is soluble, even though it says carbonate tends to be insoluble. Anything with ammonium, no exceptions, is soluble. So that one has to have a subscript of AQ. It's aqueous, it stays dissolved in the solution. Anything with sodium and also chloride tends to be soluble, but for sodium there are no exceptions. So this one has to be dissolved. Lead and carbonate, let's look at that. So I don't see a lead, but I do see a carbonate. So carbonate tends to be insoluble, except for when it's bonded with lithium, sodium, potassium, or ammonium. So lead is not one of those. So that means this is going to form a precipitate. When carbonate is bonded with lead, it forms a solid precipitate. It is insoluble. And then here's sodium again. We already know that anything that bonds with sodium is soluble, and then acetate is here too. Also no exceptions for things that are bonded with acetate, so this one is going to have an aqueous subscript as well. And then finally, one more problem here, and this is a synthesis problem that's going to bring together a lot of the concepts that we've already covered. Stoichiometry, solution stoichiometry specifically, the solubility rules, which we just went over, and then bringing back this concept of limiting reactant, because you can't get away from limiting reactant. It is always a part of reaction chemistry. You almost never have a case where you've got unlimited amounts of all reactants. So this problem says how many grams of solid precipitate will form when certain volume of a certain molarity of mercury 2 nitrate reacts with a certain volume and a certain molarity of sodium sulfide. So the first thing you need to do is write the balanced chemical equation. So this is what it looks like. You have mercury, nitrate, and you're mixing two solutions together, so you know that it's aqueous. At least the two reactants are aqueous because you're mixing two solutions together. Solution, solution. It tells you that in the problem. And then you want to look at what forms. So you do a double displacement reaction. So that means mercury bonds with sulfide, and you get the sodium bonding with the nitrate. So if we go back to the solubility rules, you'll remember that any compound that contains sodium or nitrate is soluble. No exceptions. This mercury and sulfide we haven't seen yet, so I'm going to back up to that table. Generally, things that have sulfide, S2-, are insoluble. It's paired with mercury, so the only exceptions for sulfide are lithium, sodium, potassium, and ammonium. Mercury is not one of those, so that means that this compound is going to be solid. That's your precipitate. So how many grams of precipitate will form? Now we know we're looking at this as our precipitate. And then the last thing you need to do is balance the equation, so you need to put a 2 in front of the sodium nitrate in order to balance it. So the next step with this problem, again, you're asking how many grams of solid precipitate will form. If you think back to the concept of limiting reactant, if you want to know about the amounts of products that form, you have to first determine what the limiting reactant is. Because as soon as the limiting reactant runs out, the reaction stops and product stops forming. So you have to base your calculation of grams of solid precipitate or product that forms on whatever one is the limiting reactant. So what I'm going to do to determine the limiting reactant is I'm going to ask what number of moles of each do I start with? And then I'm going to ask how many moles of the silver nitrate are needed to completely react with a certain amount of the sodium sulfide. So this is one of the differences between the non-solution chemistry limiting reactant problems and the solution chemistry limiting reactant problems. You cannot directly compare molarity to molarity, but you can compare moles to moles. So that's why I need to find moles of each reactant before I can proceed with my limiting reactant problem. So to find moles, I'm going to go back and use that technique where I've got a volume and a molarity, and I've got a volume and a molarity, and I can find moles using that if I use molarity as a conversion factor. So I'm going to start with mercury 2 nitrate. I've got 0.050 liters, and the molarity is 0.010 moles per liter. So that gives me 5.0 times 10 to the negative 4 moles of mercury nitrate. I'm going to do something similar for the other reactant, sodium sulfide. So I've got a volume of 0.020 liters of sodium sulfide, and I'm going to use the molarity, which is 0.10 moles per liter, to get me the number of moles of sodium sulfide. I've got 0.0020 moles of sodium sulfide. So now that I know, I could go to grams if I want to, but there's no reason to. You can just stay with moles of each. Now that I've got moles of each, I can figure out what my limiting reactant is. I'm going to figure out limiting reactant in a little bit of a different way for this problem, just to show you another way to do this. What I could do is just say, okay, how many moles of the mercury nitrate, if I've got that many moles of mercury nitrate, how many grams of precipitate will form? And if I've got this many moles of sodium sulfide, how many grams of precipitate will form? Or I could just say, how many moles of mercury nitrate are needed to completely react with this many moles of sodium sulfide? And if I don't have enough sodium nitrate or mercury nitrate actually present to react with this amount, I know that it's my limiting reactant. So let's see what happens. I'm going to start with the 0.0020 moles of sodium sulfide. And I'm going to figure out how many moles of mercury nitrate I need to react with that. So if I look at my balanced chemical equation, it's a 1-to-1 ratio. Right? For every 1 mole of sodium sulfide that reacts, I get 1 mole of mercury nitrate reacting. Moles of sodium sulfide cancel, and I have 0.0020 moles of mercury nitrate needed to fully react with this amount of sodium sulfide. I don't have that much. I've only got 5.0 times 10 to the negative 4. That's smaller than this number. So that tells me that mercury nitrate is my limiting reactant. So what I can now do is use this amount of my mercury nitrate to figure out how many grams of my solid precipitate or my mercury sulfide form. So one more dimensional analysis here. I take that amount of mercury nitrate that I actually have, so I have 5.0 times 10 to the negative 4 moles of mercury nitrate, and I want to figure out how much of that mercury sulfide precipitate will form. So for every 1 mole of mercury nitrate that reacts, I have 1 mole of mercury sulfide being produced. So I'm just going to formally write all this out, but you could skip this conversion factor because it's a 1-to-1. I just like to write everything out so that I'm clear with what I'm doing. This is your solid precipitate. And then you want to know grams. So I'm almost there. I just need to use the molar mass of mercury sulfide. So the molar mass of my mercury sulfide is 232.65. Mercury's pretty heavy. So I cancel out moles of mercury sulfide, moles of mercury nitrate. I'm left with, what did I write here? I want grams. That's grams of mercury sulfide. What I'm left with is 0.12 grams of mercury sulfide. So here's an example of a problem, that's your final answer, where you're combining a lot of the different concepts you've already learned.